Hello and welcome to Scale. So as you know, Scale is a community event and we couldn't have it at the prices we do without our sponsors. This particular room is sponsored by QConnect. QConnect is a small boutique that specializes in networking and building relationships within Southern California to connect top talent to our clients in the tech industry. They actually host things like Linux LA in their offices. So without further ado, here's Russell Pavlicek to give you a great, exciting talk about Zen. Thanks.
Good afternoon. How many people saw my talk yesterday in the Unit Kernel track? Just show of hands. I will warn you that there's going to be a few minutes of overlap, so please, no throwing of tomatoes or anything. Because we are going to cover a little bit of that territory here, but there's a lot of other stuff as well, so hopefully it'll be worth your while. The short slide, obligatory on who I am. I'm not going to sit here and read it to you, but basically I've been around for a very long time, and until recently, actually up until today, I was a Zen project evangelist, but as of tomorrow I'm laid off. So anyone with job opportunities, see me afterwards. That would be really, really nice. But I've been an open source advocate for a very long time, and it's one of the things that I actually enjoy immensely. But today I want to talk a little bit about the idea of innovation on a hypervisor. You know, we're used to thinking in terms of containers being the new stuff, and it is, but there's actually some very interesting things that's going on innovation-wise on a bare metal hypervisor. And innovation's one of those magic words, right? It's the thing that every time someone puts lipstick on a pig, they call it innovation. So many things are just hackneyed, placid tripe, really, when it comes to innovation. It's not supposed to be that way, but that's what's happening in the way things are being marketing. So innovation really is the ability to see something in a different way than you've seen it before. And it may be reapplying things that you've learned in a different way, but you should come up with something new and different. So it should be about borrowing from the known to make something, to create something that is currently unknown. Many innovations are just reassembling things that we've already understood. The cloud was hailed as a great innovation. But those of us who have been around for a few years kind of remember that a lot of these concepts existed on a thing called a mainframe. But they've been reapplied to a different set of hardware with a different set of rules. And because of that, it's become innovative. So that's a reasonable use of innovation. That's actually reusing something we knew, but applying it in a very different way. So the result does have to be significant. Now, in the Zen project, which is a bare metal hypervisor, we are using its nature as a bare metal hypervisor to innovate in various ways, and we'll cover some of these things in the next few minutes. One effort is Zen Automotive, which is rather interesting, the notion of having a hypervisor in your car. Things like real-time virtualization, that's something that we've never really thought about in most ways, but now there's actually a need for this. And what do you do if you have real-time jobs that have to be virtualized? ARM-based hypervisors, that's another issue. And of course, things like Unit Kernels, which are really quite interesting. So let me just back up and try to give you a little foundation. What's a bare metal hypervisor? Here's a little, textbook pictures here. This is a picture of your Type 1 or bare metal hypervisor. And it's relatively straightforward. You have hardware on the bottom. You have the hypervisor layer sitting on top of that. And then you have VMs which sit on top of that. It's a relatively straightforward model. There is a second textbook type of hypervisor, which is called a hosted or Type 2 hypervisor. And here we see that rather than having a straight hypervisor layer, there is a host operating system which provides the hypervisor function. It's embedded into the host itself. So it looks a bit different, and the flow is a bit different. Now, which is superior? Honestly, whichever one works best for you. There are two different ways of looking at the world. One is not innately superior to another, but the one you choose may allow you to do certain things more easily or with greater difficulty. So it's just two ways of looking at it. Now, where does Zen fit into this? As we said, this is a picture of the textbook Type 1. And here's a picture of the Zen architecture. Now, we notice that it's largely the same as a Type 1, but there's something missing. In the hypervisor layer itself, we do not find device drivers and device models. How many people have been around long enough to remember the good old days when you'd go to maybe it was the local computer show on a Saturday or something like this, and you'd buy that board that you really wanted to get, you'd come home and you put it in your Linux box, and you boot it up and it's, no driver. And so you'd have to see whether, if upgrading the operating system would do it, or maybe you had to go out, for those of us who remember, to SourceForge or to FreshMeat, and you had to get the driver, you had to compile it, you had to link it in, you had to build it up and see if it would work for you. The bad old days, yeah, the bad old days. Well, when the Zen project hypervisor was defined, they said, you know what? We really don't need to go through that. We don't want people to we don't want to have to keep up with every device driver that comes along. However, Linux and the BSDs already do a really nice job of doing just that. So what we'll do is we'll leverage their ability to give us device drivers. And so enters this slight change, this notion of a control domain, or DOM0, the first VM. And in there, we will leverage the drivers that exist already in the control domain. Now, the control domain could be Linux, it could be FreeBSD, it could be NetBSD, I think. There's more in the hopper. But we can leverage their device drivers so you don't have to worry about whether or not you have support. Basically, if you can load your favorite distribution up on your hardware, it'll be supported. It's really a reasonably simple way of attacking it. Now, what are the advantages of working on the bare metal space? Well, one is density. It's very, very thin. It just sits right on top of the bare metal. You don't have an entire operating system that has to be manipulated to give the hypervisor function. It has scalability. It can really support a huge number of VMs, and we'll be talking about this a little bit later. It has a nice security story. Since there is no host operating system to attack, that reduces some of the attack plane. There is the scheduling issues, which we will talk about in just a few minutes, where we can actually use custom schedulers. And in a couple of use cases, you'll see why that's really important. And then there's the notion of paravirtualization. Let me just quickly explain that one. Everyone understands hardware virtualization, right? You've got a VM, and it thinks that it's running on a piece of hardware. And if you look into that VM, you see, your NE2000 network driver, or whatever the heck it is, and it's sitting there expecting that it's going to have this hardware out there. Well, to pack up, say, your network packet into the shape of an NE2000 and pass it off to the hypervisor, which doesn't have an NE2000, which then has to unpack it and then do something useful with the data, that's wasting time. Now, it's fine if the VM doesn't know better. If the VM doesn't know that it's being virtualized, then you can use hardware virtualization. But Zen pioneered this notion of paravirtualization. If the VM can be smart enough to realize, oh, I'm a virtual machine, then what we'll do is we'll just open up very simple, very fast pipes. Basically, you just throw the data down the pipe, you wait for the response to come back. You don't have to worry about packing it up and doing all sorts of driver logic and all this other sort of stuff. It's very, very simple. And there's an advantage to that, and we'll talk about that in the use cases. So let's just take a look at some of these things in detail. Zen Automotive is a sub-project of the Zen project. Zen project is part of the Linux Foundation, for people who don't know. It's open source. Do not be confused by the commercial Xen-based products that are out there in the world. That is product, we are project, we are open source, and so, you know, always have been, always will be, and it's very straightforward there. But the Xen automotive work came along from a group called Global Logic, and they wanted to do infotainment systems in cars using a hypervisor. Why would you want a hypervisor in a car? Well, if you think about it, there's now a lot of rather discrete computers inside your average car. You've got that the rear view camera. You've got the video that's streaming to the back seat for the kiddos. You've got your OnStar button or whatever on the dash. You've got all these computer-based things, all of which have to be individually sourced, tested, installed, tested again. That's a lot of hardware, a lot of testing. And they said, well, why don't we have just a hub of processing for the infotainment system? So we'll have a computer with a hypervisor, and we will just stuff it full of those things that we need. And then we'll hook up the devices that we need, you know, the screens in the back seat and all that sort of stuff that we need to control. But we won't have to go through the testing and sourcing and et cetera of all these discrete computer systems. We'll put it together in one lump. And so they're doing this. This happens to be an ARM-based thing that they're working on. Now, there are challenges to this. Because if you think about it, things like, you know, streaming video, that's kind of real-time-ish, you know? You don't want that thing hesitating and stopping and starting because something else wants the CPU. You want a nice flowing picture. Well, that's a different sort of problem than your traditional virtualization. So you've got soft real-time support has to be there. For some things, a hard real-time support needs to be there. You have to have GPU virtualization. You know, how far we've come. 5 years ago, something that had a hypervisor would never even have a GPU. You know, most servers were headless. That's the way we ran. We didn't need graphics. But now, not only do we have the graphics, we got to virtualize that too. So that becomes tricky. We've got these other coprocessors and stuff like this, which are rather unique to this use case. We have to be able to get them supported. There's got to be a need for certification. You know, cars are tricky things. You got to make sure that it passes all this stuff. All sorts of driver support for weird things that don't exist on your average server. And even support for various operating systems that don't exist inside your normal server room. So there are lots of challenges to this. So one of the advantages of Xen inside this scenario is that it can help facilitate an extreme focus because it's not part of an operating system itself. We can leverage the fact that it is flexible enough to be focused on exactly at the task at hand. You can't just repurpose a server-based hypervisor and make this work. You have to do a lot of work for it. So, so you don't, like I said, you don't have to worry about a legacy host operating system, and you can have the flexibility to do what needs to be done. Now this leads us into the whole notion of real-time virtualization, because that's actually used by the Xen automotive stuff. And you've got efforts like RT-Xen, and there's another one, the name of which escapes me. But, you know, streaming video and stuff like this, like we said, you don't want that thing going or pixelating. It's got to be there, it's got to be there, it's got to be there. So the rules for handling those VMs has to be very well laid out. So you need a scheduler that makes sense for real-time operations. Well, Xen being type 1, it doesn't have a default scheduler that goes along with the host operating system, because there is no host operating system. Xen actually allows you to use various schedulers. And in fact, you can even have layers of granularity. So not only can you say, well, I want to use a different scheduler for this particular piece of hardware, you can say, well, I want one scheduler for these couple VMs. I want another scheduler for these few VMs over here, and so forth. It allows a great deal of flexibility. And that's the type of thing that when you're working with type 2 is going to be much harder. So here's the types of schedulers that we have out there right now. The default one that's in the hypervisor is known as credit, and it's a general purpose one. It works really well inside the data center and so forth. The one that is in development that is assumed to become the default as soon as it has all the pieces beat into it is called Credit 2. It's currently in an experimental form, and it is optimized for low latency and high VM density. And we're going to talk about why high VM density is going to be really important in just a few minutes when we talk about unit kernels. But it doesn't even stop there. We've got, oh, come on. We've got a mouse that wants to do things that I don't like. There we go. We've got other schedulers as well. The soft and firm real-time scheduler for multi-core operations, or the hard real-time scheduler for single core. So we can use different schedulers to go along with the workload. We're not limited in the way we attack the problem. We can adapt to the problem. There are also schedulers that have come, were used, and are pretty much discarded now, but most of them are still out there, and there's a list of some of them there. We've got a wiki page with all that sort of stuff on there. By the way, these slides should be up on the Scale website soon, so if you see anything of interest, you don't have to scurry to write anything down or so forth. But this actually leads then into the whole ARM-based hypervisor, because a lot of these things are leveraging the ARM architecture. How many people are working with something that eventually may be in the ARM space? Do we have any people here? Okay, there's a few people already in that area. So the virtualization extensions that were added to ARM v7 and beyond opened up a lot of possibilities for us. And architecturally, the ARM-based hypervisor theory maps beautifully with Zen. And that means that we don't have to go through mode changes. And no mode changes means greater speed, greater security. Let's see what we mean about that. Here is the architecture for ARM. And we see there's a hypervisor mode, there's a kernel mode, there's a user mode, and there's currently a device tree with various device access. Now, how does Zen play into this? Well, the hypervisor works directly in the hypervisor mode. It doesn't cross over into user mode, doesn't cross over into kernel mode. It doesn't need to inflate privilege or open the door to some sort of, possible exploit. And then the user space and kernel space from the guest VMs just maps into user and kernel mode. Hand in glove. Now, we still have one area in the device tree that isn't covered, the I/O space. What goes there? Well, domain 0, just like we said in theory, handles the drivers for the hardware. That's exactly what's going to be here. And PV being para-virtualization, like I said, that wide open pipe that makes things very fast. Since there is no legacy operating systems to worry about in the ARM world, we can just go straight to PV, which is very efficient for moving data back and forth. So it becomes a very efficient, very sweet picture architecturally. Where will an ARM hypervisor play? You name it. At Zen Developer Summit, I guess it was about 2 years ago, someone stood up and said, we want to put a hypervisor on one of these. Like, why would you put a hypervisor on a cell phone? Well, I said, think about it. In the world of bring your own device, you go to work for a big company and they say, yeah, sure, get your email and stuff like this on your phone. Of course, when you leave us, we reserve the right to issue the wipe command. And suddenly the address book, the picture of the wife, the kids, grandma's phone number, all gone. Because we need to protect our intellectual property. But what would happen if we had multiple personalities on the phone? Business you and personal you. The wipe command could take business you and remove all that stuff. But the personal you is just fine. It's intact. So as you're leaving the big company, you can be on the phone to your grandma talking about the wonderful things that you're about to do. You see it inside embedded systems. We talked a little bit about automotive. We had a talk from a guy at GE that's running hypervisors on trains. Who'd have thunk, you know? It's actually a really interesting concept. But you think about what's going on with trains. You've got this giant lumbering thing that ideally has to be able to look miles ahead on the track to stop, you know, freight train. You can't just hit the brake and not, you know, and come to a dead halt. It's not possible. But if you had a computing plant in the engine of the train with multiple VMs, and one of which is to actually test and look ahead and receive data about what's on the track, it could receive the signal that says, wait a second, there's an obstruction, begin braking now 2 miles ahead, so that you can come to a slow halt and not, you know, hammer the car or whatever else that's out there. And this is already out there in GE. You've got the things like the Internet of Things. You know, you've got lots and lots of little things, talking about millions, billions, trillions, whatever. I mean, that's huge. Basically, anytime you have a button or a switch, you can have something there that has to respond to it. Well, if you got lots of little things, then suddenly an ARM looks interesting because it's low power, it's small, and it's ideal for little responses. And then, of course, there's the whole notion of servers. You know, this one's been kind of coming and going. We'll see whether it really catches on, but ARM-based servers are a real possibility. Now let's take a look for a moment about the Unit Kernel. And this is the thing that, for me, has been one of the most exciting things inside the past year. The notion of super small VMs, very quick booting with enhanced security by design, easy deployment, and enabling transient microservices. Once again, Internet of Things, you don't want thousands and millions of things sitting out there waiting for you to press the button or turn on the light switch. You want, when you hit the button, something to say, dispatch the thing that is going to respond to it, respond and go away. That's a transient microservice. It doesn't exist until the button is pressed. Its lifetime may be a fraction of a second, where it's given birth, it responds, and it dies. And things like unit kernels make that sort of possibility happen. You know, in the world that we're used to, if you've worked with the cloud, everything right now, up until now in the cloud has been about orchestration. We had this rough, mean, slow data center where everything was static, you know, and it used to be that you could wander through a data center, and if you had the senior administrator, you know, you could just cover his eyes and he could walk down the rows and say, okay, that's the HR server, that's this, that's the database, this is the, and he didn't need to see it because it was always in the same place at the same time. In the cloud, everything's got to be flexible. And so the work has been on the cloud engine, the orchestration layer, OpenStack, CloudStack, et cetera, et cetera. And that makes perfect sense. Except the stuff that we're putting in the cloud still looks like the stuff that we had in the data center. Full images, stacks and stacks of software. It's big, it's beefy, it takes up a lot of room, it's slow to start, takes up a lot of memory, et cetera, et cetera. What if we could make it more efficient? If we could make it small? You know, right now, or at least in the old days, you were lucky if on your server, if you could manage to get into double digits of VMs at one time going on your server, it's like, oh boy, I got it. You know, I'm something special. I managed to figure out how to do that. But that's not what we want for the future. In the future, We want to look at these workloads. We want them to be easy to deploy and manage. They should have a very small footprint. Get rid of all that unnecessary duplication of code. Fast startup. Have things like transient microservices. Have higher levels of security. We got to remember, in the cloud, you know, the old status quo of security doesn't work. If you don't believe me, just check the news clippings for the past year. How many security breaches have occurred? It's horrendous. Government systems, big company systems, etc. We need something better. And ideally, we'd like to have thousands of VMs per hardware server. That would be a whole lot more efficient. Let me just stop right there. I guess it's about 10, 12 years ago now, I was working with a fellow who was building a data center in Southern Virginia. And this thing was coming together. He only had cable running like half of it. He was starting to move the racks in. And he said, you know, this place is full. Like, what do you mean this place is full? You don't even have power in half this place. What do you mean it's full? It's like, no, you don't get me. I know where every machine's going to go in this building. And when I finally get every cable run, every rack assembled, every server installed, this place is full. I will not be able to put one more server in this building. It's like, why would you build a data center with no room for expansion? So, because I went to the power company, and I said, how much power can you give me? They said, that's it. Not a watt more. So I built the data center to use that much power. Because if we want anything more than that, we got to go somewhere else and build another data center. We think in the cloud, oh yeah, you know, I go out on Amazon, and if I need more, I just say, give me more. It just keeps coming and coming and coming and coming. But in reality, power is limited. These servers have to be powered up. They have to be cooled, which takes even more power. So you've got all these things that are physical limitations. If we can make it more efficient, then that data center, which was maxed out and couldn't do one more thing, suddenly would have room to do all sorts of additional things. He would have loved it. But that was then, this is now. But that's where we're going with this. Now, we've got Docker and containers, and they've done some tremendous stuff. They made the deployment so much easier. They got that smaller footprint together, which is really nice. Less memory, less disk, very fast startup times, high numbers of VMs per host. Really good stuff. Lots of steps in exactly the right direction. But there's still some issues that are being worked on. You know, once again, you're sharing a kernel, so you're not going to run your Windows instance on your Linux-based container system, you know, so you got to do stuff like that. Not a big deal. There are potential limits to scalability. You know, Linux is really, really flexible. But it's not really, you know, it wasn't designed to be doing thousands of processes quite in the way that containers do, but it gets the job done. But security, that's kind of the big issue. And they're working on some really good security mechanisms. But, you know, I find myself thinking of every time that I've seen an administrator deploy a server with SE Linux installed on it, and the first thing he does is to turn it off because it takes too long to configure. And the boss said, get that server up now. Oh, I'll get to it. I'll get to it. You know, you'll get to it when that server ends up being, you know, thrown off the loading dock in a few years. There's been so many that are like that because if the security is added on, we got to make sure that it's as easy as the deployment model. Ideally, the security should be baked into the pie so that you don't even have to think about it too much, if at all. Well, that's where the unit kernels come in and do some very interesting things. They're also very small, very efficient, very quick to boot. And they've got a security element to them, which is unlike anything else that's in the industry right now. Anyone that's ever tried to lobby for green technology, say, all we have to do is invest so much money and then we'll get return on investment in 9 months. You know that that can be a really tough hill to climb. But the interesting thing is that once you get into stuff like this, the return on investment tends to be almost immediate. It's a lot easier to convince people to go that way. Now, there's a number of various unit kernels out there. We will look at them extremely quickly. So what really is a unit kernel? And I borrowed this from the Mirage folks. Thank you, Richard. Unit kernels are specialized virtual machine images compiled from the modular stack of application code, system libraries, and configuration. Well, think, well, that's just like any VM, except that this is one executable, one blob, not layer upon layer, one blob, single address space. Let's take a look at how this plays out. This is the development picture. And during development, this is actually, pretty standard. You take the configuration files, application, binary, language, runtime, you compile that together, and you create a blob that sits on top of a Linux and or Unix-like operating system, and you test. Well, that's pretty straightforward. That's pretty much what we're doing now. Nothing really new about that. But then you get into the full testing scenario, and suddenly you're doing all of these things through the kernel threads, the user process, the file system, network stack. All of that comes together in one singular package. And that is sitting on top of Linux and or Unix-like operating system for testing purposes. But then you get into the deployment scenario, and the picture changes just a little again. All that stuff is compiled together, but now it sits directly on top of the hypervisor, which sits directly on top of the hardware. What's missing? The operating system. There is no operating system. There are just the needed operating system functions that happen to be compiled into the unit kernel ball. And those ones aren't a full operating system. It is simply those individual pieces that are required to make that thing go. Nothing more. So here's kind of the concept. You want just enough to do the job. You don't need multiple users, right? I mean, if it's going to be some sort of database system, if it's going to be a web server, whatever, you don't need something to be able to log in and walk around and have multiple. There's no need for that. So get rid of that. You don't need a general purpose operating system. You don't need 10,000 utilities. Why? If you want it to be a web server, let it be a web server. That's it. Get rid of all the rest of that stuff. Because you know that when the malicious hackers come, that's what they use to try to bust you. So we'll just get rid of it entirely. We'll remove their toolkit. And you don't even have a full set of operating system functions, like I said. You have only what's needed for that thing to exist. So it's very lean, very mean, minimal waste, very tiny size. So how does, this is like an embedded system theory. Do we have any embedded programmers here, or people who at least have been? Hello, Richard. Okay, in the back too. So this is basically applying the concept of embedded programming into the data center. So it's not really a new concept, but once again, it's that innovation of taking what's already existing and applying it to something, to a scenario that's never had it before. So you've got some things that you have to account for. One of which is that obviously you're not going to have a debugger sitting there. You're not going to have all sorts of tools to debug things. You say, oh, this is terrible. How am I going to be able to do this? Well, when you think about it, when you're in production, at least most of the production servers I've worked with, the owner of that server doesn't want you to be able to sit there, doesn't want you to sit there and debug on his production system. He says, take the data, take the logs, bring it over your test box, find out what the problem is, fix it, and make sure it doesn't happen again. So you're basically in the same scenario. You just have to make sure that the stuff that you can pull off the production system is enough that you can do the debugging elsewhere, because you're probably not doing your debugging on your production box anyway. So that's kind of a trade-off in order to get these ultralight images. What do the results look like? Well, here's some things from Mirage. A fully functional DNS server for 449 kilobytes. Some of us with the gray in the temples need to turn to some of the young people and explain what a kilobyte is. Because it's not gigabytes, it's not terabytes or petabytes or kilobytes. Most of us haven't said the word in 15 years. You know, a web server, 674 kilobytes. OpenFlow Learning Switch, less than 400 kilobytes. Ling, another one of the Unit Kernels. Boot time to shell under 100 milliseconds, that's really kind of an old spec. Most of the time they talk about 20 to 30 milliseconds. Erlang on zen.org, which is where Ling hangs out. They eat their own dog food. They've got a Unit kernel running that page, and if you click up in the corner, they'll show you what they're using. And when I clicked on it one day, I ended up seeing that it was using 8.7 megabytes of memory to do the job. If you have a web server that's using 8.7 megabytes of memory, suddenly the notion of having thousands on a single host, not so far-fetched. If it's small enough, you can pack them in there. ClickOS from the NEC people. They have network devices that will do in excess of 5 million packets per second. We had a really nice talk from some of the NEC, from one of the NEC people yesterday in the Unit kernel track. Once again, average size. These are also somewhat older numbers. I think he said that right now it's about 5 megabytes of memory and closer to 20 milliseconds of boot time. We're talking about very small, very fast, and functional. It's a different world. Now what about security? Type-safe solution stack. You know, when the first set of Unit kernels came out, they were inside these type-safe languages, you know, sort of esoteric things, and it's like, you know, there's Haskell and there's Camel and, you know, all these things that, like, who uses these languages, blah, 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 blah. But the thing is, there's actually a need for that, for some things, maybe not for everything. But suddenly, you've got the possibility of a stack that can be certified. About 2 years ago at Zen Project Developer Summit, and it's available online at zenproject.org inside the videos section, there was a talk given about software certification. You know, you got like a fly-by-wire system, something that has to be tested because it's life or death. They said if you had a Linux stack, it would take millions and millions of dollars. It would take years upon years, and by the time you were done, it would all be useless. You need something small, ideally with a type-safe language, but suddenly that becomes very possible in the Unit kernel world. You also have image footprints that are now unique to the image. Not only do they lack the utilities and things like this for malicious hackers to do, but you don't even know what the image footprint looks like. You don't know what functions are. But to do something then, if you do manage to break it, which requires a lot more cleverness than it does now, is an incredibly difficult task. Because you have no utilities, you have no blueprint, you've got nothing to work with. So you have no utilities, you have no shell. You don't even know what libraries you can work with. Here's a very partial list of some of the Unit kernels out there now. Mirage OS from the Zen Project Incubator. This team, a number of them, put together a company called Unit Kernel Systems, which you may have just read was acquired by Docker. You know, you got some serious things going on there. We had a very nice talk yesterday about interfacing Docker with Unit kernels. So I think there's a really nice story that's brewing there, and I think that crew in particular is going to move that ball forward. HAL VM from Galois, Ling from Erlang on Zen, ClickOS from NEC, OSV from what was Cloudius, and now, I forget its name now, but they're database people, but you know, it's actually a really interesting thing, but since it's open source, it doesn't matter whether the company's gone onto a different direction or not. It's open source, it's still very usable. Rump Run, which is really cool from the Rump Kernel project. And that's just the beginning. There's even like about 3 more that I didn't put on here. Basically, every time I've had to do this talk, I have to go back and check because the number of unit kernels is just expanding. People are working with it. They're coming up with new concepts. So how does Zen project enable this? Well, because there isn't a host operating system, it's type 1, it means it's lean and mean. We don't have to make any assumptions about the way the hypervisor is going to behave. So that VM can sit on a very thin hypervisor layer, which can then be tailored to the needs of those VMs. The attack surface is very, very small from a security standpoint. You have great scale-out support. I think these numbers are a little old. The last number I saw was that the goal is to try to get, of some of the engineers, is to try to get 2,000 to 3,000 VMs being able to be deployed linearly with no degradation. And the last number I saw was 600. I think it's up from that. Basically, they're constantly going back, looking at the architecture of the hypervisor and saying, how can we improve it to make thousands of VMs a reality in terms of absolute linear performance. That's one thing that is, it's one thing to have the science experiment that says, oh yeah, well we can do it. But it's another to make it really perform well. And that's what Zen is doing. We have the enhanced credit 2 scheduler. It's part of the reason why it exists out there. As I said, part of its new life is to be able to facilitate potentially thousands of very small VMs. And you want it to be able to work on ARM as well. So is this all in the innovation world with Zen? No, actually there's tons of other stuff that I'm not even going to be able to touch on. Virtualized GPUs, there's been a whole bunch of stuff in that area. Enhanced NUMA. Colo, I think, is still out there. The notion of a coarse-grained lockstepping of VMs. For people who remember the old tandem systems, those of us with gray in the temples, where you had 2 systems that would sit there together. One would die, and within 30 milliseconds, that second one was up with the exact state of its predecessor. So basically, uninterrupted, no loss of data. That's what Colo is trying to do. And things like native VMDK support. And we've got an innovations page out there for people who want to look into it. So here's kind of a review. So these are some of the advantages that we see working in a bare metal state. We can support very high density. We can support a very high number of scalability, high scalability of VMs. We don't have a host OS that can be attacked. We can rework the scheduling to go along with the need. And we can use the simplified para-virtualized interface to make things easier. That's especially interesting if you look at the history of the unit kernels. Most of them started on Zen. Why? Because Zen had the para-virtualization state. Because it's really easy to write a PV driver. Open hole, throw data down, wait for data to come back. If you have to sit there inside some other hypervisor that's going to make you write a hardware driver, that's a lot more work. And it's a lot less efficient. So it's been one of the wins in this area. So, tomorrow's workloads are not yesterday's workloads. We tend to think of hypervisors as plumbing in the world of clouds now, right? It's like, oh, every house has to have plumbing, but once you got it, you don't think about it. Nothing could be further from the truth. If your hypervisor isn't keeping abreast of your needs, if it's not moving where your data center is moving, you're going to have a problem. And that's one of the things that the project is very much trying to do. We want to stay ahead of the curve. We want to implement some of these new concepts and make sure that when people need it, it's there. So we're trying to get the next generation together. That's the end of my presentation. Any questions? In the back. Is there any difference between XenRT and Xen other than the scheduler? To my knowledge, it's the scheduler plus some other things, but I'm not an RT person. But they've, they're looking at the full ball of wax there. So I think it is more than just the scheduler that's being addressed, but I can't swear to it. I don't see. Richard, are you? Well, Xen on ARM run on a Tegra. Offhand, I don't know. It's an A15. I'm not the right person to ask, quite honestly. There is a wiki page that describes the various things that are supported right now. I just don't have it memorized, I'm sorry. Did I answer your question or not? I'm trying to. There is also, one of the interesting things inside the Xen world particularly, if you go to the wiki.zenproject.org, if you need to know anything, just, if you want to know about XenRT, plug that in. Chances are you're going to get some information out of it. We try to keep stuff out there, and if it's not out there, we need to know so that we can work on it. And XenRT is still, and there's actually like 2 different real-time efforts, and I don't know who's winning right now. They're both designed a little differently. If you see Lars Kurt, who is here at the conference, I tended to work mostly with the user base and less with the developers, so but he has got his thumb on the development stuff, so he would know which ones are coming along and what they consist of. Sir? Again? Some of the people who were responsible for Mirage formed a company called Unit Kernel Systems, which has been purchased by Docker. So there are a number of Mirage-related people who now work for Docker. And we had a talk yesterday in the Unit Kernel track about actually doing the demo showing Mirage running under Docker, being deployed and stuff like this. Well, no containers. No containers. Just using the Docker APIs, the Docker command set, to the Unit kernel directly. So we're not using containers at all inside that case. It's just deploying Unit kernels on a hypervisor, but using the familiar Docker interface. Well, if it's all using Docker, it shouldn't need to. I mean, it's actually, it's all working with the Docker API. It's just re-implementing it so that the Unit kernel is being dispatched instead of a container being dispatched. So if you have a Docker-based infrastructure, in theory, now this is still, from what I gather, still sort of work in progress and stuff like this, and sort of a proof of concept. I think it was displayed at DockerCon, but they've showed that it's very possible. It does work. Let me get him and then you. In the back. Okay, I'm not sure I quite get. Each of these is actually a VM. So each one can or may have, an IP address associated with it. If it has a network stack, which most of the time you kind of figure it would, but that's up to you. Depends on what it's doing. Yeah. So I mean, these are real, honest-to-goodness VMs. They're just really, really small, and they don't have a lot of gunk in them. So the rules really haven't changed. It's just the way it's being put together that's very different than before. Ma'am.
Is it possible or thinkable that this will use multiprocessors, real, honest-to-God multi-hardware? I mean, multi-nodes offered by, let's say, Intel or not?
Yeah, this could be.
Will they use the innovation that Intel has put in there for the use of virtualization, like extended page tables or TLB modification?
Well, from the hypervisor layer, the question is all these. What was that? Yeah. The question, as I understand it, has to do with there's all this new hardware support that Intel and others are putting into the servers. Can all of these things be leveraged in this scenario? Insofar as the hypervisor is using them, yes. Insofar as the VM is using them, in most cases, it's not even using virtual memory. There's no need for it because it's a tiny static thing. So it doesn't need all of these advanced functions. Now, you say, well, then why do we have it? Well, because there are going to be lots of things that are not going to be unikernels. You may have your big honking databases, you've got all sorts of highly complex processing, SAP things. They're going to need all of that stuff. But does your Apache web server need it? Probably not. So that's the sort of thing that we're making a distinction between those small, manageable workloads that we can make nice and small and keep them small. And then we can free up all that resource to be used for those big things that really do need that bleeding edge technology and need masses and masses of memory and all that high-end performance stuff. So it's not that none of that matters. It's that we give to who needs it and don't waste for things that don't need it.
I never thought about it in that way. I've never seen something that doesn't run perfectly.
So, yeah, it's a, once again, since it's dealing with an embedded concept, you think about, an embedded program in a device, it doesn't need a fancy operating system. It doesn't need virtual memory. It just needs to do what it's supposed to do, gets the data in, throws the data out, and that's it. And there's a lot of stuff that we do in the computing center right now that do exactly that, but they've got this gigantic infrastructure. Let's get rid of the gigantic infrastructure. Let's keep it simple. And then we can take all that infrastructure that is now being wasted and put it towards those really big things that require it. So it's a reallocation of resource, basically. Sir?
Amazon is into big time with them. Are they also trying to work
Amazon, well, I know Amazon is become quite active inside the Zen developer community. Exactly what they're doing in the unikernel world, I'm not exactly sure. But I think it's safe to say that they're aware of what's going on. So, maybe it's not this month, but I would hesitate to say that it's never coming. I mean, it is possible to deploy unikernels on Amazon. There's some papers out there right now. Unfortunately, you end up having to use a lot bigger machine instance right now than you need to. But, some of these ones, if they come up with a unikernel-sized VM, that may not be as much of a problem.
Yeah. So do me a favor. Raise your hand for questions. I'm going to try to get on the mic. That's a, any more questions?
Uh, to me, it's that this works on ARM. I do a lot of embedded stuff. Does it take advantage of the memory protection?
I'm afraid I'm having a very hard time. Just project to me and I'll see if I can. Okay, does it take advantage of memory protection on some ARM processor? Honestly, I don't know. The developer guys are better at that than I am. Like I said, I've tended to work with the user base, but if you come across Lars Kurt, he probably could answer that question. If you want to help, how do you get involved? Go to zenproject.org. That's probably the best way. That's sort of the hub of the Zen Project universe. You'll find information about the mailing lists that are out there. We've got two very active lists, Zen users and Zen Devil. You start with Zen users and say, this is what I'm looking to do, and can I help, and so forth. But we have an extensive wiki out there as well with information on how to do this or that and how to get involved with various things. So, spend a little time just sort of wandering the wiki and you will get a lot of information, and ask questions on Zen users and you will get pushed in the right direction. We also have, a couple IRC channels and stuff like this. All of that, you go to zenproject.org and look at that. It will give you information. What are we for time here? Okay. Do we have in the back? How does the Unit Kernel approach affect the storage infrastructure issue? Is that what I heard? Yeah, that's one of the things that's sort of under active development, because some of these things, I mean, there is the capability of using storage. Basically you compile in just the file system that you want to use or whatever. It's probably the weakest area right now. May or may not be the best fit for things as they sit at the moment. But there's so much going on that I expect to see a whole lot more in that area. Because not everything requires extensive file stuff, and sometimes a little re-architecture, things that you'd write to disk instead, if you're throwing it across to another VM, which records or whatever like this, might make sense. It kind of depends. But there is support inside a few unit kernels for writing things out. Not always the most efficient in the world at the moment, but it's being worked on. Sir.
How closely do the RT projects and kind of the main one track each other? They completely separate, or are there plans to convert?
Well, there's always the hope of, the question is, how does RT project converge with the main one, or how does it track with the main one? There's always the hope for convergence. But like I said, I think there's actually two different RT things. I don't know if they're both active right now. Lars would know. That are out there that have been working together. They're both trying to solve problems, and the hope is that one of them is going to be the sort of the preferred real-time methodology. But this being open source, one of the beauties of open source is that if you have an idea and if I have an idea, we can both explore our ideas and let the best idea win. So that's one of the really nice things about this, is that we don't have to agree up front. There is no company that's making a decision on the way it's going to be, blah, 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 blah. Let's go at it and see who comes up with something that works best. So, is it going to converge? We hope so. And there's a lot of work, I'm sure, going on in that area. If you come across Lars Kurt, I'm sure he can talk to that more extensively than I can. He is the community manager in particular. He deals with the developers, which I generally don't do very much. My apologies. Going once, going twice. We're at the end of the hour. Thank you very much for spending the afternoon with me.